Today we're going to talk about beats when it comes to mixing two waves. It has several applications. It's a relatively simple idea. Applications can be from tuning instruments. Pilots of twin-engine aircraft use this concept to know if their engines are going at the same speed. Also work in mechanical systems, and we'll see it with pendulums here. So beats occur when you have two waves of similar frequency, similar wavelength. So if you look here on the screen, we have at the top, we have the blue wave, which is F1, has a frequency of 257 hertz. And the red wave is also 257 hertz. And the bottom, the purple wave, is the addition of the other two waves. So if you look here in the middle, this one's the blue one's at a crest at the same point. The red one's at a crest, and that adds up, and you get really high crest. And then here we have a trough, and that gives you a really low trough. And so they add up, and we can see that when we overlay them, the two sit on each other just perfectly. When you hear that, you won't hear anything different. You just hear two tones that are 257. What becomes interesting is that when you change the frequency of one of them, so let's put it like such, they don't look terribly different. The blue one's at 235.2, bottom one's at 257. And when you play them together, what you're going to notice is that they sound a little different. You get that pulsing sound. And the more similar they are, you get a definite pulse. That's called the beat. Well, let's take a look at it in this situation. The beat is pretty fast. And if you overlay them, what you'll see is that here in the middle, we have crest on crest, trough on trough, get large amplitude for the sum. But over here on the left, they are completely out of phase. The red one here is at a crest, the blue one's at a trough, and that would add up to 0. Okay. Likewise, over here on the right, we have red ones at a crest, blue ones at a trough. They would add up to 0. They basically cancel each other out. And so what we get is we get a region which is very quiet here on the far left. Then we get constructive interference. It's very loud. And then we have a destructive interference, very quiet. And as it goes from quiet to loud to quiet to loud, we get this pulsing. And that is the beat frequency. However, if we get them much closer together, get that definite beat frequency. And this can tell you when the beat frequency slows down, when there's no beat, we know they're in tune. So you can tune two instruments and listen for the beat, and as the beat gets slower and slower and slower, you know they're getting in tune. If you have twin engines, and these twin engines, you want them to spin at the same rate, if you hear that pulsing, you know they're close, but they're not quite there. Okay, so that's the beat frequency and why it occurs. Now, we're going to give you a little bit of mathematics. It's relatively simple, and then I'm going to do some problems for you. Okay, so really simple. What we got is the beat frequency is simply going to be the difference between the two frequencies. Okay, and we're going to take the absolute value because we don't care if it's positive or negative. We always want it to be positive. So if F1 is bigger than F2, that's great. If not, we're just going to take the positive value. And that's really all you got to do. Also, if you want to find that, remember the period of the beat would be the reciprocal of the frequency. Okay, so period and frequency are reciprocals of one another. Okay, so let's try some simple problems here. And the key is going to be kind of a diagram to help you stay organized. But it's really simple, basic idea. If you had 257 hertz and the other one was 255 hertz, the beat frequency would be 2 hertz. Now, The problem can be is if you know that, hey, I know one of them is 257 and the other one, when they play together, it gets 2 hertz. Well, if you know that one is 257, 2 hertz could end up giving you 255, or it could give you 259. It could be 2 more or 2 less. And so the absolute value doesn't, if you just know the beat frequency and you know one of the other frequencies, you don't know exactly what the second frequency is. You simply know it's either going to be plus the beat or minus the beat. So 257 minus 2 or 257 plus 2, okay? So let's take a look at these problems here, and we'll see, show you how these go. Diagram's kind of helpful. Tone X and tone Y are played together, and a beat frequency of 5 hertz is heard. Tone Y and Z are played together, and a 10 hertz beat is heard. Find all the possible frequencies for X and Y if the frequency for Z is 400. So what we're going to do here is we're going to say that Z is 400 hertz. And then when you play Y and Z together, you get a 10 hertz beat. So we don't know what Y is. We know it has 2 options. It's either 10 more or 10 less than 400. So it's either let's make that 390 hertz or 410. And then when we have X and Y are played together, we hear 5 hertz. So we come here, we can say, oh, that would be either 385, 395, plus or minus 5 on here would be 405 or 415. So all the possible frequencies for X and Y, there are 4 different frequencies we could get for X, and there are 2 different frequencies we could get for Y. That's all you got to do. In number 2, we have X and Y are played together. We get 5 hertz beat. Y and Z give you 3 hertz. X and T give you 6, and Z is 650. So this is just going to have more layers to this. We have Z is going to be 650 hertz, and then Y and Z are played together, and you get 3. So we go plus or minus 3, which is 647, and 653. We don't know which one it is. The beats don't tell you if it's higher or lower. It simply tells you the difference. And then we know that X and Y are played together, and that's a difference of 5. So we're going to get 642, 652, plus or minus 5, 648, and 658. And then we know when X and T are played together, that's a plus or minus 6. So we're going to have T down here, and that's going to give you 636. Plus 6 would be 648. If we take the 652 and subtract 6, we get 646. If we add 6, we get 658. Likewise, from the 648, we get 642. And we get 654. And here we get 652 or 664. So it says find all the possible values for T. So there's 8 values for T. Okay, now let's try another one. Number 3, we have X is 300 hertz. And then what we do is we say when X and Y, let's say X and Z is 6. So what we get is 294 or 306. But now we have X and Y is 5. So that would be 295 or 305. But the question is, find all the possible beat frequencies for Y and Z. Okay, so this is Y down here. So if these are the two values for Y, they would give you a beat frequency of 1. That's Y and Z. If these are the two, that would give you a value of 11. There's a difference between them of 11. If we did the 306 and the 295, that would be 11. And if we do here, that's only a difference of 1. So really, your frequency of the beats is going to be 1 or 11 hertz. That's all it's going to be. Okay. Now, let's take a look at a system here where we have two pendulums. Okay, so we're going to look at a short little video on the two pendulums. We have two simple pendulums here. We have a long one with a longer period of vibration and a lower frequency. And we have a shorter simple pendulum which has a shorter period and a higher frequency. When you put them together, you'll notice they start together, they get out of sequence, and they come back in. By knowing the frequency of the individual ones, subtracting those two frequencies, that gives you the frequency of the beats. And the reciprocal of the frequency of the beat is the period of the beat, or the time between when they're together and when they get together again. We have two simple pendulums here. Okay. So now let's go back to this problem. We have two pendulums swinging next to each other. One makes 10 oscillations in 11.7 seconds, while the other makes 10 oscillations in 10.3 seconds. Find the frequency of each pendulum. So in order to find the frequency, we're simply going to take the number of events divided by time. So one of the frequencies is going to be 10 divided by 11.7. 10 divided by 11.7 would be 0.855 hertz. And then the frequency of the other one will be 10 oscillations in 10.3. It's going to be just slightly less than 1. 0.971 hertz. Okay. The beat frequency is simply going to be the difference between them, absolute value. Okay, so we simply subtract those two, and you get 0.116 hertz. That's the beat frequency. And then the time between the moments when the pendulums are swinging together. So in the video, you notice there are times when the pendulums are swinging together, and then they get to the point where they're going opposite each other, they're completely out of phase, and then they come back together and do that again. To find the time it takes to going together and going out and coming back together, that time between there is the period of the beat, which is the reciprocal of the beat frequency, which is the reciprocal of the 0.116, which is going to be about 8.5 seconds. So with these pendulums, it would, in about 4.3 seconds, they would be going completely opposite from each other, and then another 4.3 seconds, they'd be back. A total of 8.6 seconds to get back from in phase to out of phase and back again. So I hope this helps you with all the problems.